Good morning, everyone. My name is Federico, and I'm going to talk about the sixth chapter of the book Steel Metallurgy, developed by Doctors Boniardi and Casaroli. The chapter is called Iron-Carbon Phase Diagram. Here is shown an iron-carbon phase diagram, and that allows us to see the phases of the alloy under conditions of thermodynamic equilibrium to changes of temperature and carbon content. Remember that any chemical system is defined as being in thermodynamic equilibrium if all the thermodynamic variables that contribute to describing it don't change over time. We can also observe the three structural transformations listed here on the right and make an important distinction between iron-carbon alloys. Still, if carbon content is lower than 2.11%, cast iron if greater. In addition to the blue liquid phase here on the top of the diagram, there are other four one-phase fields. A very limited green alpha phase field on the left here, a large extension yellow gamma phase field here, a very limited brown delta phase field here, and finally a red iron carbide phase field on the right vertical axis of the diagram here. Like shown, the iron-carbon phase diagram is truncated at 6.69% of carbon. Moreover, it is assumed that carbon is soluble in the liquid throughout the entire extension of the diagram. Note that iron carbide is a metal-stable compound, so it tends to decompose into iron and graphite carbon. However, the decomposition takes so long that in practice it can be neglected. We now start with eutectoid steel having a carbon content of 0.77%. Starting from the liquid phase, initial solidification occurs between TL and TS with the formation of homogeneous gamma phase crystals. Subsequently, the alloy undergoes the eutectoid transformation at 727 Celsius degrees here. These transformations involve the transformation of homogeneous crystals of gamma phase in crystals of a lamellar nature, with alternating lamella of alpha and iron carbide phases. At room temperature, the system is totally composed of lamellar crystals, and the two phases can be calculated with the lever rule. Have a look now in what happens for hypoeutectoid steel that usually crosses the area of perithetic horizontal at 1495 Celsius degrees. What is important is that there can be three different phases transformation. Here, we can see them here, depending on the carbon content, like explained on the right. However, below a certain temperature, the system is entirely composed of homogeneous crystals of gamma phase. Whereas this kind of steel has a greater iron content compared to eutectoid steel, an infinitesimal degree above 727 Celsius degrees, the alloy is composed of homogeneous crystals of alpha phase and homogeneous crystals of gamma phase. Instead, at 727 Celsius degrees, we can observe homogeneous crystals of alpha phase and lamellar crystals with alternating layers of alpha phase and carbides. This is also the final structure at room temperature. Finally, the case of hypereutectoid steel that forms homogeneous crystals of gamma phase without crossing the perithetic or the eutectic horizontal. Since it has a greater carbon content than eutectoid steel, the excess carbon is reduced between T1 and 727 Celsius degrees, with the formation of iron carbide phase on the grain boundaries of homogeneous crystals of gamma phase, like shown here. At 727 Celsius degrees, the iron carbide phase on grain boundaries remains unchanged, while there is the transformation from homogeneous crystals of gamma phase to lamellar grains composed of alternating layers of alpha phase and iron carbides, like shown here. At room temperature, the structure results unchanged. From what just seen, it is possible to conclude that there are three types of microstructures: homogeneous grains, lamellar grains, plates on grain boundary. And moreover, the phases and microstructures of steel are usually indicated as austenite with reference to homogeneous grains of gamma phase, ferrite with reference to homogeneous grains of alpha phase, perlite with reference to lamellar grains composed of alternating layers of alpha phase and iron carbide phase, cementite with reference to plates of iron carbide phase at the grain boundaries of homogeneous crystals or lamellar crystals. Remember these because are very important in the following. So, at 20 degrees Celsius and in conditions of thermodynamic equilibrium, excuse me, the microstructures are composed of perlite for eutectoid steel, ferrite and perlite for hypoeutectoid steel, and perlite and cementite for hypereutectoid steel, with the various amounts that can be calculated always with the lever rule. Steel undergoes an important transformation at the solid phase, and we can see there are three critical points indicating the transformation of gamma phase, and are defined according to the carbon content. They are A3 from austenite to ferrite, A1 from austenite to perlite, and ACM from austenite to cementite. If critical points are determined in conditions of thermodynamic equilibrium, they are indicated with letter E. But they can also be determined in conditions of non-equilibrium, and in this case they are indicated with the letter C or R, respectively for heating or cooling conditions. This is due to the thermal hysteresis that can cause an increase in critical points with respect to equilibrium in the heating phase or a decrease in the cooling phase. In all kinds of steels there are always present also other alloying elements, and they can be austenitizing if they tend to expand gamma phase field, like manganese, nickel, carbon, copper, or ferritizing if they tend to expand alpha phase field, like titanium, chromium, molybdenum, and so on. The austenitizing or ferritizing action of the alloying elements is not only function of the alloying element's content, but it also depends on the alloying element's type. For example, we can see that the ferritizing effect of titanium is much higher than chromium. Note, finally, that the alloying elements can raise the eutectoid temperature in case of ferritizing elements, or lower it in case of austenitizing elements. The critical points will be modified by alloying elements, and they can be calculated through the following empirical formulas by Andrew, shown here at the bottom. Thank you for the attention.